thank you very much for the invitation to this course. Yes, I will start sharing my screen. Can you see it?
Yes, very well.
All right, so I was asked to present something about battery energy systems. As Björn said, I am a professor in chemical engineering, and I have a PhD degree from inorganic chemistry, so I'm a pure chemist. And I expect maybe not all of you are chemists, so therefore it will be a little bit of chemistry in this lecture, just to get the background of what are the possibilities that we can use chemistry and in energy systems, that we have this conversion from electricity to materials. Just a short what I will talk about. So I will give a very short background in the storage application in the grid. I suppose that is covered by other lectures, and you are more experts on that than I am. Then I will just give a little bit of a background to battery. What is an electrochemical cell? Where do we get the current from? What is the potential? What properties do we have of a battery, and how can we play with the battery design to reach these different properties? And then I will go more into detail when it comes to lithium-ion battery, since that is the major battery today, I would say. And then in the end, I will cover some other battery systems. I will mention a little bit about electrolysis and a fuel cell, what that is. And I know that there is another lecture then more on the use of hydrogen. And then I will end the whole presentation with something about redox flow batteries. Yes. So energy storage, and what can we do when we have overconsumption, overproduction, for instance, of energy, and how can we store that? And there are some different options, and either you can just use the electricity and convert it into some chemicals, so that you use that to produce something. And I suppose the most common is that you can produce hydrogen. You can also produce, you can reduce the CO2, for instance. You can do fertilizer. You can do different chemicals. And there are other, you can produce heat, of course. And then you can store the electricity in a chemical, and then you can convert it back to electricity if you need that. And so there are different options, but I will only go through the electrochemical steps. And since we are increasing the amount of renewables, this is an increasing problem, because before, when we produced electricity from a fuel, we could change the process when we have ups and downs in consumption, but now we have to rely on the nature what we get. So this is from European Commission, and here are some, they have listed some what we should use, what the different services we have in the grid. And there are services in the short range of time, frequency regulations, the quality of the voltage of in the grid, etc. And all from that all the way to where we really want to shift loads in different seasons. Maybe we have a cold winter, and we have lots of sun in the summer. How can we shift energy and electricity over to the winter, for instance. So there are lots of different services, and I would say it's not clearly sorted out what type of storage we should have in different. I mean, one can see that different storage is differently useful in different applications, but really to see what is the best way is not really set right yet. And there are some, and here you see my pointer here. Here are, for instance, one can do such a graph where we have the power versus the time scale. So you see here that, for instance, for very fast time scales, then capacitors, ultra capacitors, supercapacitors are a good choice, and in very large powers, energies, and for hours maybe pumped hydro is the best. And in between there are lots of different ways. Some are electrochemical and some are other type of systems. Nevertheless, these should not cost too much to install. And here are some European goals, then the prices that you can expect for both in the more like in a virtual power plant where connected to the producers up, and here more for the residential, for buildings like private storage. And then we can expect a slightly higher price for this. And here in the last graph here, you see some different applications. And of course, there is an increasing demand. The more solar and the more wind we will install, there will be a larger demand. So the last picture again, and now I have just connected here the different types we are working with. And here you see the difference in the construction of these different systems. They're all electrochemical cells. A battery have large electrodes. You store the energy within the device. In a flow battery, you have instead tanks, so you store the energy outside the electrochemical cell. The cell is made smaller. For an electrolyzer, there are different types, but the most common is the alkaline, and then you in principle have electrodes that you have in solution that is pumped through, and then finally in a fuel cell you pump in hydrogen and air into a cell, and that is also can be made smaller than a battery where you have to store all the materials in the cell. I will come back to this, but these two different systems are also different fast in their response, and the supercapacitor is where you only have a reaction on the actual surface of the electrode and not in the bulk material. Then it have a very fast response. Lithium-ion battery has a poorer capacity, but also a relatively fast response. The fuel cell and the redox flow battery has a lower, shorter response, but can store more energy in principle. But of course, these are still not for the very large energy storage, I would say. And yeah, you see here the background, the blue curve here is the use, the demand. And here the red curve is the light if you have solar panels. And you see there is a mismatch that they are not, and that has to be solved. And just an example that what we have in Sweden so far, this is something that is built up in Sweden, where I think we are a little bit later than other countries, since we still have hydro turbines up north, and that could be working as you can regulate the production from there. But we have seen in some cities that we have a shortage sometimes, and in Uppsala now, Vattenfall is building a plant or a storage, and that is with lithium-ion battery, new batteries, and and of course this will be researched on to see how they can be used and etc. So to some fundamentals. So what is a battery, and what can it and why a battery? So you know that we can't store electrons and electricity in itself, but they can be converted to something else, and we can convert it into a chemical, and that could be either a solid material or a liquid. Then this conversion between electricity and matter can then be made in an electrochemical cell. And if we produce electricity from materials, then we have a galvanic cell. We have somehow the energy in the materials, and then spontaneously electricity come out from this, and then we call it galvanic cell after Galvani, that's invented electrochemistry. And if we have such a battery, we call it a primary battery. That's a non-rechargeable battery. And if we produce materials from electricity, then it's not a spontaneous reaction. We call it an electrolytic cell. And an example of that is a water splitting electrolyzer. A rechargeable battery is then called a secondary battery, and it's reversible. So it can go in both directions. So it can both be galvanic when we discharge it, so then it's spontaneous and works towards equilibria. And when we charge it, it's electrolytic, and it's non-spontaneous, and it walks away from equilibria conditions. And the battery word, what does it come from? In the older days, we call it accumulator. It's the same thing. Battery is a military term, and it can be used both for a large storage device, or we call it, or for a single cell. So there is a broad word in that sense. So what is an electrochemical cell then? In principle, there are, if you combine two materials with different nobility, you can then create a potential difference between those if you connect it like this. The strive to reach equilibria, to exchange electrons between the materials, is then giving rise to the flow of electrons, which is the electricity. So we have a reaction on the electrode, and we call that charge transfer, and these are the electrodes. And they have to be supported on a conductive support, and that is the current collector. And then we have to have migration of ions in a liquid, or it could also be a solid electrolyte, but we have to have migration of ions and some conductivity here for it to work. Then we also have to have ion conduction between the anode and the cathode. So we have to have, here is a salt bridge. It can be a membrane, it can also be a separator, but somehow we have to have ionic conduction between those. And finally, we also, of course, have to have electronic conduction in an outer circuit here in order to be able to use the electricity. So this is needed. Of course, you can simplify it and have the same electrolyte and then have the anode and the cathode closer to each other. And we can have lower losses and higher currents. We also, so the two electrodes here has to be different, and I prefer to call it a negative electrode. That is the electrode with lowest potential. If we have discharge, then it's the anode at the negative, and we have always oxidation at the anode, and we have a release of electrons. At the positive electrode, that is the more noble material, that is called cathode at discharge, and we always have a reduction at the cathode, and that is the uptake of electrons. In principle, if you would run this as an electrolytic cell, then the anode and the cathode swap side. But in battery, I should say that people call the positive electrode for the cathode, even though it's run the opposite direction. That is something to keep in mind. It's a little bit hard to sort that out. All right, we can, in principle, all electrochemical reactions can be listed and ranked like this. If we measure the potential versus a hydrogen electrode, we get a potential, and then we can list it like this. And you see here that the very ignoble materials, lithium is in the bottom here at the very low potential. And we have high potential materials up here, noble materials. Now, this is not the whole list of the periodic table, but it can be made a whole list in principle. Yes, and this is done at standard conditions. And if we then, for instance, take something here as this example we had before, we have copper deposition. We form copper from copper ions that has this potential, and then we have a dissolution of zinc and forming zinc 2+, and then it goes in the other direction. So the two electrons that we produce here or consume here are produced in this reaction. And the difference in potential here, this is the cell voltage. And this is, of course, theoretically, and this at the standard conditions, but this is the maximum potential that you can expect from this type of system. So from that, you can understand that if we take lithium here with a very low potential and something very up here with a very high potential, we can have a large cell potential. But we cannot go outside it because this is the elements and this is the material that we have on our planet. So this is what we have to play with. So shortly, what is chemical potential? That is an electromotive force and an energy difference per mole. As a chemist, you prefer to work with mole, and therefore you see here you have Faraday's constant and the number of electrons, and that gives the Gibbs free energy. And you see here the relation to entropy and heat in this reaction, if you have forgotten that. And at standard conditions, this is linked also to the standard, the equilibrium constant for the reaction, and also really you have to take into account the temperature and also the gas constant. And this together gives the famous Nernst equation. So, so you see here that the potential is the standard potential that we just talked about, and the term which is related to the concentration of the elements. So this is a bit shifted down or upwards depending on the concentration ratio you have in your solution. And yeah, sometimes it's written like this with log instead of ln. Here you see an example that if we have for cadmium, for instance, we have the reduced side in the formula, that is cadmium here, 0 is the oxidation state, divided with cadmium 2+, which is the ion. And sometimes it's written the opposite, so you have a plus and then you swap the side in the division. And so this was the potential, so that is given. So what we also have is the current, of course, and what is determined then the current, and that is the flow of electrons through the circuit. And of course, it depends on the electrode surfaces, because this is heterogeneous reactions, so it all take place on the surface. And a good way to increase the surface is then to have a porous electrode. Here is an example of a lithium-ion, cross-section of a lithium-ion battery. And yeah, the more sides you have, the more place you can have the reaction, and the higher flow of current. And of course, the rate of reaction is also important. Some materials are slow and some are fast. And then we can have other losses. We can have iron drop, for instance, if we have low conductivity in the electrolyte. And then, of course, in a battery, you consume or you react to all the material, then of course you cannot do any more reactions, and then we have a concentration limitation, and then the flow of current stops. So an example of this, here we have a typical lead acid battery. You see here we have a lead on one side, and we'll have a lead oxide on the other, and this is the oxidation state of this lead oxide is 4. And then we have a sulfuric acid in the electrolyte, and when this happens, then we have a reaction between the lead and sulfate, and we form a compound called lead sulfate. That is a solid, and it has a certain potential. And at the negative, and yeah, I should go back to here, the oxidation, what happens is that lead go from 0 to lead 2+, so you have an oxidation reaction. On the other side, we have a reduction from the lead 4 to lead 2, and this lead 4 oxide is reacting with the sulfates and forming the same compound as we had on the negative electrode here. And but this happens at much higher potential, and actually the difference in potential is over 2 volt. And here you see how this can look like. It keeps here its higher voltage, because this is it's a cell with several. It's a battery with several cells connected. So therefore we have higher voltage. But you see here, in principle, you have almost the same potential until you have used up your materials. Of course, you will have a change in sulfate concentration, and according to Nernst's equation, then we can expect to have a drop in potential as we discharge it. So typically a discharge curve looks like this. We have an average potential, which in reality is slightly lower than what we theoretically have shown. But that is quite stable as long as we have material, and then when we used up the material, it drops. And the capacity of the cell is then the charge, the integral of this curve. So it is the current that we use for discharge and times the time. And that is equal then to the Faraday constant times the number of moles and the electrons. So this can be calculated also theoretically. Generally in a battery, you don't want to really discharge it, so you stop at a certain point, and that is set by the electronics. If you have the capacity per kilo, then we call it specific capacity. And here you see that the energy is then the capacity times the voltage, and the power is the current at a certain point times the voltage. So from this you can understand that the higher cell voltage and the larger cell, larger surface area, the higher energy in your system. And as you have just a fixed amount of material, of course, if you discharge it at a very high current, then it goes faster to discharge it, etc. And a lower current, then you can use it longer time. That is quite obvious. But in order to be able to compare different type of systems, different type of cells, we use nowadays something called C rate. That is the current normalized to the capacity. So it's defined like this, that 1 C corresponds to the time, the current it needs to discharge the battery 1 hour. And of course then a half C, then it takes 2 hours to discharge. 2 C takes a half an hour to discharge. Something also much used in battery world is state of charge and depth of the charge. It's in principle the same thing, it's just that you state of charge is, we talk about fully charged is 100%, and depth of the charge is then is fully discharged 100%. And here you see the charge curve and discharge curve, and generally we are only using part of this curve because we don't want to the extremes here, because that could stress the materials and we can have irreversible changes. So what you see on your telephone when it's fully charged is probably not fully charged, it's just charged up to a certain amount that is set by the electronics. And we also talk about Coulombic efficiency, and that is how well the charge, the losses that we have when we charge and discharge many times. If we have a small loss every time, then we have a loss in efficiency, and that is a sign of that the system is not very stable. We have bireactions, etc. So some different common battery types. Yeah, you knew all that we have the primary battery, the alkaline battery, and that it has a zinc negative and a manganese oxide as a positive. And here is the reaction. It has a cell voltage of 1.5, and here are the theoretical and real specific capacities and energies. We also use this lithium and manganese oxide in these small cells that we have for clocks or whatever, and that has a higher energy, of course, since it has lithium, because it has a high cell voltage. Then we have the secondary batteries, and those are the rechargeable, and I've already talked about lead acid. We have nickel cadmium that is not used so much any longer. Nickel metal hydride is a common battery, and then of course lithium ion battery. The Zebra battery is not used so much, even though it is a quite clever idea. There are of course many other types of batteries, but those are the most common. You can go back later on and look into the specific figures here, but you see, for instance, that the energy density is highest for the lithium ion battery, much higher than for the other types. So a little bit about the development. I said those older systems, lead acid and nickel cadmium, came 100 years ago or before that. And then in the 70s, we got the nickel metal hydride. In the 90s, the lithium ion battery. And maybe you remember that we had the Nobel Prize 2019 with these three men as inventors. And you see, for all these types, we have higher specific power and higher energy density. But the question is how long can we really go here in this? We can probably extend it slightly more, but we are anyhow limited to the periodic table. We don't have more elements than we have there. Something about the differences here. But for the older types of battery, we always used water-based electrolytes. So either in strong base, like the alkaline battery, or in strong acid, as the lead acid battery, and there are also examples of salt concentrations. And it is like so that the water is decomposed into hydrogen gas or oxygen gas if we extend the potential window larger than 1.2, 1.3. Either that we in the low pH regions or in the high pH regions. And that means that if we can combine the metals with a larger difference in potential and we have a water-based electrolyte, then we will anyway, then we will start to decompose water and we will have problems with oxygen formation or hydrogen formation. And that will cause a risk and yeah, we can have problems. And we have, for instance, self-discharge with a lead acid battery. But on the other hand, these are chemicals that we have and it's safe and we know it has good conductivity, easily handled, etc., etc. But we have, from our perspective, we have too low cell voltages, too low energy, too large batteries, not useful for vehicles, for instance. What this new invention with the lithium-ion battery was, the main part of this is that we can have an electrolyte that is organic. And that means that it's stable in a much larger potential window. We have no reaction whatsoever in a large window. And typical such are these carbonates, different chemicals. The problem here is that we cannot dissolve high concentration of the salts, so the conductivity is quite poor. And these solvents, they are flammable and sensitive to air and water. And that brings in that we have lower safety, it's more expensive, it's more problematic to recycle, etc., etc. So we have the high voltage and high energies can make small and light batteries, but it is a concern with the safety. So a little bit more into lithium-ion battery. I said we have this organic electrolyte. What we also have is that we have intercalating materials. So instead of lithium, like the lead acid material where we form a new compound, lead sulfate, here we can just insert the lithium between these layers, and in principle the material is the same. And when we do that, we oxidize or reduce the metal that we have here, which is commonly cobalt, manganese, iron. It could be different transition metals. So we use that redox change, and then we insert the lithium or desert. And the same thing on the negative side, where we can have graphite And here also between the planes in the graphite we can insert. And when we take it out, we have not changed much the structure of this. And that makes it very durable. We can continue to charge and discharge many, many times. So this is a common way of showing it, but in real, we have grains of these materials, and we have also have carbon to help for the conduction, and the electrolyte is then in all these parts. So we have a porous electrode on both sides. The charge and discharge curve looks like this. So the black here is the complete cell, and the dotted here we have here is lithium cobalt oxide, the potential for that, and down here we have the graphite when it's intercalated. And the design of these cells is that you have the porous positive electrode, the metal oxide, on an aluminium current collector, and then you have a separator, and then you have the graphite on a copper current collector. And generally you have on both sides. And then you make a roll of this, you see here, and you can put it in a cylindrical cell like this. You can also make a flat roll, and then it's called prismatic, or you can have sheets. So there are some different types. But if you don't have it in a roll, then you have to have some press the cells together so that you have good contact through all. Depending on the design of the battery, you can either have it energy optimized or power optimized. And for high energy, you should have as much active materials as possible and as little inactive materials as possible. And you make thick electrodes, large particles. For high power, you make thin layers with small particles. You have large surface areas, so you can reach high currents at a short time. This means that you have lots of inactive material, and then we have a lower energy in this type. But depending on what application, for instance, if you have a hybrid electric car, then you prefer to have maybe a power optimizer, this type of battery. While, for instance, for energy, pure energy application, you prefer this type of battery. And then, of course, you can combine cells. So if you combine a typical module has 12 to 16 cells in series, and then we can reach a higher voltage. And in such a module, you also have a little bit of cell supervision. You measure temperature, voltage, etc. And in a car, you have a full pack, and then you will combine several modules. And then you also have a battery management systems. And of course, in this battery pack, you also have all the electronics, cooling, etc., etc. So a little bit more on, as you see here, I'm not too late, on the materials and the mechanisms that we have. So yeah, you can have different type of reactions in the active material. I mentioned the lead sulfate, which is a conversion material. And then we have insertion in the lithium ion battery, and then we call it intercalation, is when the lithium goes into holes. And here is some different types, and the most common is the layer type. So here in the blue parts here, this is the metal oxide, and then you can add lithium in between these layers. And you see, they can diffuse either from from the A or B direction. But not in the C direction. But the increase in size is only happening in C direction when we intercalate. Spinel is a more complicated structure. Here you can introduce the lithium ion from all sides, and in the olivine you can only introduce it from one side. So this, of course, gives different properties when it comes to diffusion into these materials. Here is just listed the most common. Often you see these abbreviations for them and the structure. I can mention that NCA is what we have in Tesla battery, for instance. LFP is, of course, more abundant with iron. It's more common maybe in buses, etc. NMC is what is mostly used today. LCO, what we used to have in electronics. And you see they have a little bit difference in potential and capacity, and also the discharge curve has a little bit different structure depending on what materials that we have. But I should mention that the average potential here is determined by the metals that we have. And if you have several redox active materials, then of course we can have like a slope. We can use all of that. For the negative side, I said that the graphite is the dominated, that is a layered structure. We also have something called lithium titanate oxide, LTO, which has excellent rates, but has a much higher potential. Now also silica is which can be alloyed, then we can increase the capacity drastically, and that is also inserted in the graphite. So you have a composite electrode in quite many cells today, I would say. The intercalation into graphite is stepwise, so that gives the discharge curve has these features. So you can see how much has been intercalated in the material with this structure change. I should also mention that I said that these organic electrolytes are very stable. They are, but they actually react with the graphite, forming something called SEI layer, solid electrolyte interface. And that adds resistance to the cell, and actually consumes some of the capacity when we form the cell with the very first cycle that is done. So this is good to know that this exists. Then when we discharge or charge at a higher rate, then we lose capacity like this. The reason to this is called polarization. It also happens when we go to lower temperatures. And this is an effect of that. The system has no time to reach equilibrium. So it actually has no time to use up all the capacity and reach the same voltage. We have more losses in the system. And the losses can either be activation and polarization, that is that we need a certain energy to go from reactions through the charge transfer. We need some extra energy to pass this activation. We also have ohmic drop, and we have polarization concentration. The lithium ion should diffuse into the solid material. We have also transports in the bulk. Something that is much talked about nowadays is also lithium plating. If the fusion is slow, then instead of reaction, we can start to plate lithium. And if that is happening, then we can fold dendrites like this and we can have a shortcut. And that could lead then to explosion. And what can happen is then we produce heat, and when the heat is produced, the organic solvents start to react, and we can have a runaway, and we have these accidents that we have heard about. We actually have very much energy in the material, in the solvents that can burn. And I won't go through, but there are lots of different aging mechanisms. But in principle, one can talk about loss of anodic material, loss of cathodic material, and loss of cyclable lithium. And that is generally due to this SEI formation of the graphite. We can expect that the battery becomes better. Here is a very good review. And more that the design is better, but also that we use them in a better sense. You can read more if you are interested. But for instance, here is just an example of the pack performance for some different automotive cars. That we see a large, this is maybe not fully updated. We see also a large cost reduction. And for the future, maybe we also go to solid state lithium-ion battery, and that means that we have no solvents any longer. So we have a solid electrolyte, and with that we can have some type of bipolar configuration, and that would be safer, but it would also introduce lots of problems, lower conductivity, difficulties to manufacture, interface resistances between recyclability, etc. There are also attempts to combine electrochemical double layer capacitors with lithium-ion battery, and the capacitor, then you only charge the surface, you don't use the materials within. But you can one of the electrodes can then be exchanged to a battery material, and then we can have the benefits of both the high power and more energy. However, there is a problem with lithium-ion battery, and that is that now we see this as the solution for automotive and cars, but that means that we will need very much raw material. Cobalt and graphite is critical, and also there are limitations in lithium. Maybe we should use this lithium-ion battery to vehicles where we need high energies to very high energy densities, and also specific energies, I mean per kilo and per volume, and use other systems for stationary. Here is just the DOE strategy for how we also should think about how we can recycle and use, but now when it's an increase, we have to use materials from mines. So shortly, other types, yes. For larger vehicles, as I said in the beginning, a battery is larger than a fuel cell, for instance. So if you think about a larger car, or a bus, or a larger vehicle, then maybe it's clever to have a smaller fuel cell and a tank for the fuel instead of having a battery in the whole bottom of the car here. And even more than for maybe an aircraft or so. So then you have to think about, how can we solve this, or can there be combinations? So just shortly, what is an electrolyzer and a fuel cell? In principle, it's the same as a battery, but what is different is that it's like an open battery. You add the fuel release. You can collect hydrogen that is formed in an electrolyzer, and you can release oxygen and water in a fuel cell. So it's like an open battery. And what is the difference is here that you use a catalyst. So on the electrode surfaces, you need the catalyst: platinum for a fuel cell and iridium for electrolyzer generally. And the cell can be stacked and made much smaller than a battery. And the capacity then is dependent on how much fuel do you add outside, or how large are your tanks. So another option is to use a redox flow battery, as I said. So here you also have tanks, but it's a closed system, so it's not, you don't tank it. This is closed from air, so to say. You have two different species, and you separate them with a membrane. So the design is very similar to a fuel cell. And here you see here's a one single lab cell where you have a sheet of porous carbon on both sides, and then a membrane and a flow field on the plates. And yeah, you have a reaction on the negative side and at the positive, and the curve looks like this. It's quite similar. You have to think about Nernst's equation also here. The good thing for this is that the power is determined by the cell and the capacity of the tanks, so that could be scaled independently for your design. And the reactions are relatively fast, so you don't need any catalyst. And here is some example. Here's a stack, and you can combine it with solar plants like this. And you from China may be familiar with this very large installation in Dalian with a vanadium redox flow battery. So to the vanadium is the most common one. And here we have the two couples, vanadium 5 and 4 on one side, and vanadium 2 and 3. Unfortunately, there are very few elements in the periodic table that have so many different oxidation states that we can use. So vanadium is quite unique. And therefore, if we have some crossover here, it's not a problem. It's the same element. And that's why these can last over 20 years, and the electrolyte can be used in affinity. We have a high solubility in acid and a quite good temperature range. And there are some other good kinetics, etc., etc. But vanadium is scarce, and the energy density is limited, and the scarcity makes it quite expensive. And here you see that the electrolyte, the vanadium in itself, it stands for 1/3 of the whole system. And here you see the countries that produce vanadium, which also is a toxic material. So yeah. So other options here, as I said before, that we have a window where water is stable. And here we can find a vanadium. There are some other elements, and I would say all have been tested. But what we want to have is materials that are not pricey. And we see here that there are not so many of them. Then there are also development in other types of batteries. For instance, we are working in my research group with this concept with manganese in solution. And then hydrogen on the other side. So that is like a fuel cell on this side, or reverse the fuel cell and manganese. A very common system is also brom zinc, where we have a metal on one side and a brom solution on the other side. And then there are different research projects with slurries or suspensions, and typically these can also be organic and of type lithium-ion battery types. There are also other types. Here is development of some different types. This is not perfectly new, but what is coming very much nowadays is organic molecules that can be redox active. But unfortunately, those are not as stable as the inorganic. And then, of course, one has to try to reach high concentrations and green electrolyte in general. And membrane is also a key question, and that is also a topic in our research group. So to finish up, I just want to do a comparison here with some different systems and how fast they act. And see here the type about the flow reader is a very many ways, maybe not for the largest systems for monthly storage. And if we compare finally the price, we see here that here we have the flow battery, vanadium and zinc bromine. But here you see that they are quite similar in cost for the lithium-ion battery chemistries. And the second one here is in 30 years and the other is 2016. You see the comparison here. So future will tell what systems we will have in the future. So what I want to say is that battery will be, I think, in balancing the grid. And now at least it seems like the inorganic battery electrodes and electrolytes are more stable, but it's important to think about abundance and safety and recyclability. And lithium-ion battery has the highest energy density, indeed, but is also expensive and sensitive and have a limited lifetime. For grid applications, I think we should open up our eyes and look into other type of system, water-based, when we have more space, and maybe hydrogen storage or flow batteries here can be interesting. But so far the installations are quite few, and we have quite little experience of what these different cell types can serve with in the grid, and how they can be used in a clever way and a sustainable way. So much more research is needed, both to look into systems that are already there, how they can be used best, but also to investigate in new types of systems. All right, maybe I used over my time.
That's fine, as we are having lunch afterwards, so we have why I didn't stop you. Otherwise, I would have stopped you before. Thank you, Rakel. A very interesting presentation. I think I'm personally